Now, gases are pretty easy to model since they're basically just solitary atoms, but solids are a lot harder because the atoms are actually interacting with each other through bonding. And so we have to figure out, where do bonds come from? How do they work? And how do the individual atoms interact with one another? That is all a story for another time. Right now, we're going to be setting the very foundation. We can't talk about the atom if we don't know where to start. So what I'm doing is I'm taking a bunch of electrons that don't even interact with one another. The interaction term is for next time. And I'm setting them in a giant box where they are free to move around with one another. And I'm just going to be studying the outcomes of the Schrödinger equation in this giant rectangular box. So here's what we're going to do. We're going to set one of the corners of this box to the origin. And let's see. We have, let's say 0 is less than, or there's going to have to be a lot of conditions here. 0 is less than, x is less than, no, not less than or equal to Lx, 0. 0 is less than y is less than Ly, 0. Or what's it? 0 and else infinity. There we go. So this potential is basically telling us that these electrons are stuck in this box, and with no amount of velocity can they ever get out. I mean, that's a pretty good description of a solid. Most of the time, you don't see solids spontaneously combust. So, how do we work with this? Well, it's time to actually whip out the Schrödinger equation. This tells us H, the Hamiltonian, which in this case is this, because we haven't factored in the interaction between electrons, is equal to some energy times psi. So we're doing fine so far. The good thing is, in Cartesian coordinates, since we're dealing with a box and a potential that's not dependent on radius, it is a much better idea to actually split things into Cartesian coordinates. So let's say psi x, y, z actually becomes x of x, y of y, and z of z. When we do that, we get minus h bar squared over 2m multiplied by what? X double prime, hold up. Yeah, that's true. X double prime yz plus xy double prime z plus xyz double prime. And this is all equal to what's on the other end, exyz. So now what you want to do is, there should be a potential term. Was it over here? Yeah, I think it was. So now here's what we're going to do. We're going to erase this, it's useless. Divide both sides by xyz, like we always do when executing separation of variables. And we get minus h bar squared over 2m, x prime prime over x, plus y prime prime over y, plus z prime prime over z, the potential. Now here's the funny part. This is equal to 0 within the box. So what this, well, if this is equal to 0, then that means minus h bar squared, hold up, no, something's up. Oh yeah, that's what I forgot. The Hamiltonian is not just this. Okay, so the Schrödinger equation always looks like this, right? Now the Hamiltonian is minus h bar squared over 2m multiplied by the Laplacian plus the potential. Which means that what you actually have, is it minus? Yeah, I think it's minus the potential. Which means what you actually have here is plus u psi is equal to e psi. So what happens there is that within the box, this just becomes equal to e. And of course, if a function of x, y, and z is equal to a constant, that means each of the individual functions within it, so minus h bar squared over 2m, or here's what we're going to do. what I can do is take these two and move them to the other side, which would mean that minus h bar squared over 2m x double prime over x is equal to e plus h bar squared over 2m y double prime over y plus z double prime over z. Now this is a function of x, that is a function of y and z. By cyclic permutation, you can also make sure y is a constant and the z is a constant. So that means all of these terms, minus h bar squared over 2m x prime prime over x is equal to c, all of these are constant and equal to one another. So I'll just leave it the way it is. So we get that x prime prime is equal to 2m minus 2m over h bar cx. So what that tells us is that, here's what we're going to do. X is equal to, we have a linear solution, sorry, not a linear solution, sinusoidal solution, which gives us sine of the square root of 2m over h bar, the square root of 2m over h bar, since this would be h bar squared, the square root of 2mc over h bar x plus cosine the square root of 2mc over h bar x. That should work. And of course, y and z are just this, but we substitute in y and z instead. So here's the thing. Here's the principle of the thing. When you look at the boundary conditions here, you realize that the particle can never be at 0, 0, 0. At that point, it's going to be pushed away by an infinite force before it ever reaches 0, 0, 0. Remember, this is not a less than or equal to sign. So, what that means is that at 0, this has to be 0. That has to be 0. This has to be 0 as well. So, x of x has to be 0, which means that, well, oh, there has to be amplitudes. Crap. So, since x is equal to 0 at the origin, that means that, well, not just at the origin, but over the entire plane, z is equal to 0, z has to be equal to 0. Over the entire plane, y is equal to 0, y has to be equal to 0. Over the whole plane, x is equal to 0, x has to be equal to 0. Which means, over all these planes, if this is equal to 0 at x of 0, or y of 0, or z of 0, this term is always equal to 0. Because this is just going to give you cosine of 0, which is 1, which means bx has to be equal to 0. So bx disappears, by disappears, bz disappears. And so all you're left with solutions. Ax sine of this, you get a y sine of this, and you get a z sine of this. And of course, you've also side of the boundary conditions for the same trick to figure out more about the amplitudes. At Lx, Ly, or Lz, this also has to go to 0. And, well, that means sine of the square root of 2mc over h bar. Well, what's going to be in here? Nobody knows. Is it going to be Lx, or Ly, or Lz? And that has to be equal to 0. So what that tells us is that so what does this tell us? Well, it's essentially telling us that Lx, Ly, and Lz have to take on a range of values. When is sign equal to 0? Either it's 0, which this obviously can't be because then Lx would be equal to 0, and that doesn't make sense because that would make this inequality impossible, or pi. So if whatever's inside these parents is pi, then everything makes sense. So the square root of 2mc over h bar li is equal to pi. And so that tells us li, or you can go this way, c is equal to pi squared over 2 h bar squared pi squared over 2m li. This is what we have. And of course, that also gives you the illusion that Lx is equal to Ly is equal to Lz. So for right now, this is a fairly fine model of the wave function, right? Because let's think about it. Now the wave function inside is why did I put these? The wave function inside is going to be ax, ay, az sine square root of 2mc over h bar squared x sine square root of 2mc over h bar y sine square root of 2mc over h bar squared z. And on the outside, we're going to get 0. And things are going good for us so far, because this has a determinate integral over the entirety of r cubed. Which means that we can actually normalize this wave function. If our wave functions come out normalizable, that means our wave functions have physical meaning. And that also means that we're on the right track. So this is the model of the electron solid when we take into account absolutely nothing other than the Schrödinger equation. Tomorrow, we're going to explore what happens when you actually pay attention to what the electrons are doing to each other. We're going to talk about variable 2. What happens, remember, that these electrons are part of a system that includes protons that are also interacting with one another. Until then, well, I'll see you next time. Thanks everyone for watching, and we'll see you in the next one.